Hey, what's up, guys? This is Chung here. It's been a while. Okay, so this time, LeetCode number 1923, longest common subpath. Okay, so this time there's we have n cities numbered from 0 to n-1 in this country. Okay, so I'm going to skip this long description, right? So in the end, what we have is we have a list of lists, okay, and then we need to find basically the longest common subarray among all the list. So that's what this problem is all about, right? So if you read this long description, so if you translate into a programming idea here, basically we're given like a list of lists, and then we need to find the longest subarray, the longest common subarray among all the list. Okay, that's why in this example one here, right? So n is 5, and then so actually I'm not quite sure if this n helps or not. Basically n is 5, and then we have this 3 arrays here, and the answer is 2 because we have the longest common subarray is 2 and 3, right? Because as you guys can see, 3 appears in all the path, right? And then in example 2 here, the answer is 0 because obviously since each array only has one element and there's no common array here, subarray here, that's why the answer is 0. Okay. And this one is 1 because there's actually either one of them is fine. Basically, either 0 or 1 or 2 or 3 or 4. Any of them will will give us the same answer, right? Okay, cool. So that's that, and that's the constraints, right? So first we will have like at the most n numbers. Sorry, n numbers where n is a 10 to the power of 5, right? So the m, so the length of the path is also like 10 to the power of 5, right? And then here the total sum of the length, the total sum of the element, the cities, is also within 10 to the power of 5, right? So that's it, right? So and obviously given this constraints here, we cannot use any brute force way to solve this problem. Basically, we can't simply just find all the subarrays, right, and then try to use that subarray to look from the others in the other arrays, and then we try to find a common one. So what turns out to be is that this problem is like a binary search problem because the idea is this. We're looking for the longest common subarray, right? So if we have, let's say if we have if we have a middle, if I have this kind of this answer, basically anything smaller, the middle, will also be a common subarray, right? So for example, if we have 2 and 3, the answer is 2, then it means that definitely has 1 as a common subarray as well, right? So that's why if this thing is true, then we can use a binary search. Basically, we simply binary search the final answer, the length of the final answer, right? And then we check if we can find any subarray, any common subarray with that length across all the paths, right? Then we're gonna return true, right? And then we just use binary search to find out the longest one, right? So the binary search idea is not that difficult, but the difficulty for this one is that given like a fixed length, let's say a fixed length of a subarray, how can we efficiently check all the paths, right? So basically what we can do here is that we can use a rolling hash, right? Basically, I think so. What's that algorithm called? I think Rabin carp, if I remember correctly, right? basically we just use your rolling hash, basically what shall we do? So first, for each of the path. Okay, oh, and one more thing. So for the binary search, we have a left and right boundaries. For left, obviously it's 0, right? How about the right? Right is the minimum of all the list. Basically the minimum length among all the list, because the common one cannot be greater than the smallest one, right? Okay, so that's the boundaries. And now, given like a length, how can we use rolling hash to check across all the path or all the sublist? So basically, what we can do is that for each of the array here, right? We store all the rolling hash with the length of middle, right? We store that into a set. Okay, let's say we call it set A, right? And then we do it with a set B with another list here, right? Then we have set B, right? And then we simply just need to find the intersection, right? We need to find the intersection of these two. Intersection, right? With this intersection, we use this intersection to intersect with the set B here, set C, right? So we basically every time when we have like for each of the lists here, we'll have like a set, right? We'll have a set who stores all the rolling hash value for this list, right? And then we always do an intersect with the previous result, and in the end we just check if there's anything left in this intersection set. If it is, then we return true. Otherwise, return false. So that's basically how we do it. And yeah, so that's that. And about rolling hash, right? So about rolling hash, and since we have a pretty big number here, right? Basically, we could have like a rolling hash with like a number with like 10 to the power of 5 digits. Obviously, we cannot represent a value with this big, right? So that's why we need to do a mod. Okay, so that's the first thing. And the second one is that how about the base, right? So for the rolling hash, I think I already talked about some rolling hash problems, in my previous videos. Basically, for the rolling hash, we also need like a base, right? So in our case, we have a base of, usually, if it's like 8 to z. If it's A to Z, right, obviously the base will be 26, right? Or at least 26, because we want this one to be representing that. But for this one, we have, see, so basically the biggest, okay, so the biggest number we are looking at, it could be 10 to the power of 5, right? That's why our base should be at least bigger than the biggest values. That's why for us, in our case, we can choose the base equals to what? Equals to 10 to the power of 5 plus 1. So why do we need to do a plus 1, right? So for the base, because so first is that the base has to be at least as big as the biggest number. Second one is that we need to it's better to choose a prime value, a prime number, because we don't want to have like 10 to the power of 5, because otherwise if we only do this, right, if we do a multiply later on, it's gonna be we're gonna have like a lot of hashing collision, right? So that's why when we choose like a base, remember there's two rules. So first is we choose a number at least as big as the maximum possible number. Second one is we want to choose like a prime number. Okay, so that's that. And yeah, I think that's it, right? I mean, with that being said, I guess we can start coding, right? So first, the two boundaries, left and right, right? right is going to be the minimum of the length of the path for path in paths, right? So that's the right boundaries, which is the minimum length of all the list. And then the binary search template, we already talked about this many times. Okay, r minus left divided by 2. Okay, so we have a helper, right? Helper is going to be the one, right? If this one is true, cool. So now since we're getting the maximum one, which means that if it's true, then it means that left is going to be the middle, right? Else is going to be the right is going to be the middle minus 1, right? Again, this is because since we're trying to get the maximum, that's why we're trying to push the left boundaries as far to the right as possible, right? And since this one could be the answer, that's why we do this. Otherwise, if we're getting the minimum, then we are going to push the right boundaries to the left as possible, right? So that's how we do this binary search. And then, yeah, just return either L or R in the end, right? Pretty simple. So that's one. And the tricky part is how to implement helper functions, right? So basically, these helper functions, like I said, it takes in a middle. This middle actually is the length of the common subarray. Okay, and we want to check if there's at least one common subarray with this length exists across all the list. Okay, and in order to do that, let's say we need to like the base, like I said, right? So it has to be as big as the maximum values, right? So I'll just use this one because the biggest one could be a 10 to the power of 5, right? So that's and the plus 1 to make it as a primary number. And then we have a mod, right? The mod is also something we have to be consider because since we're going to do a lot of multiplications, right? We need this mod to, and so the mod for me, I just simply change this one to chose like a big enough numbers. Actually in the end, this problem is not. It's kind of like a randomized problem based on the test cases, right? If the test cases are complicated enough, right, or edge cases enough, then we may need to choose a different model, the mod or base, or even like different hashing functions. Okay, but at least for this one, I chose this one as a mod. Okay, and then we have a hash set, right? So that's the global hash set that we in the end we're gonna check. So what does it mean? It means that basically we will return in the end if the length of the hash set is greater than 0. So this hash set stores the common subarray who has this size equals to middle. Okay, and so for I.path in enumerate. Okay, so now let's enumerate each path. Okay, and for each path, we need a hash set 2, right? Because we're gonna do an intersect later on, and then we're gonna have current hash equal to 0. Right, so now for j in range of length of the path. So to do the path, actually, this is a very common one. Basically, the formula is like this. So the current hash equals to the current hash, right, times base, right, plus the number, which is the path.j, right, and then minus, right, minus what? Minus the path dot j minus middle, right? That's going to be the length, and then times base, right, to the power of the middle, right? So that's basically the whole formula, right? Like for example, I think I already demonstrated this one some many times. Let's say if it's a simple 10 base, right? We have 3, 2, 1, right? So now we are having we're having like a 4 in this case. So how do we get, if the length is 3, right? If the length is 3 and then we have 4 here, so after 4 we instead of 321 we should have 214. This is the one we're getting, right? How can we transform from this one to the 3 to 1 to 2 to 1 3? So obviously what do? We do the previously hash function times base. In this case it's 10 base because it's easier, right? This one, right? Then plus what? Plus 4, right? Plus 4. This is how we get 3,214, right? And now we need to subtract what? Subtract 3,000, right? After this, we're gonna have like 214. So what is 3,000? 3,000 is this, basically 3 times what? Times base, right? Base is 10. 10 to the power of what? Of 3, right? So that's how we get 3,000, and that's how we transform this expression into this code, right? So that's the basic idea of the rolling hash with different base. But of course, in our case, our base is much bigger. So that's that. But there are like some improvements we can make. First is this one. This thing, right? The base to the power of this middle could be a big number, and this one could be overflowing our result. That's why for this one, it's better for us to pre-calculate it and also with like a mod. That's why I'm going to use like a here. Going to be I'll just use the power function in Python. Basically, the base. The second one is the mid, and third one is the mod, right? So in this case, this one is pre-calculated, and we can simply do this, right? But so here, we will only be doing this thing when the j is greater than the middle, right? Otherwise, we will simply just keep increasing, calculating the hash until it reaches this middle. Then that's when we need to start doing this. So I guess we can, and then we can just maybe separate this one into 2 parts, right? So first part is this one, and then basically if the j is either equal or greater than the middle, right? That's then when we need to subtract. Okay, gonna be a path, right? Dot j minus middle times a, right? And then don't forget to do a rolling the modular of mod, right? And then yeah, we need to store everything into the hash set 2, right? For the current list. Basically, if the j is either equal or greater than the middle minus 1, right? And then we add it into the hash set 2. Add it. Then this current hash, right? Uppercase, I guess. Okay, and then in the end we need to do the intersect. So we can, so if the first one we don't need to do the intersect. If the first one we simply add this one to the hash set 2, right? And then else, else we do intersect. Hash set goes to hash set intersection of hash set 2, right? There's like a small trick here. Actually, I was, at the beginning, I was, instead of doing this, I was checking this. So if this length is empty, it's 0, and then I do this. Otherwise, I do this. But there's a bug here, Basically, if after some intersection, if this one becomes to 0, right, and then if we do this, this one will become to a non-zero, right? So that's why we shouldn't do this. Instead, we should do this. I equals 0, right? And yep, so that's that, and yeah, so that's it. Actually, there's a like small improvement we can do here. Basically, if I is greater than 1, if I is greater than greater than 0, and the hash set is equal to 0, and then it means that we don't need to continue here, right? We can simply break, right? Basically, if the I is greater than 0 and not hash set, right, and we simply break because there's no need to continue, right? Because this one is already empty. We are sure there's no common one. But this one will not affect the the time complexity. Yeah, so that's it, right? So that's the basic idea of this rolling hash problem. If we run this one, let's see. Oh, there's one thing I forgot. So remember, every time when L is equal to middle, don't forget to do a +1, right? Okay, so now accept it. If I run it, let's see. See, so we got a wrong answer because this one is pretty big, right? We got this a big number, but we only expected this one here. So most likely, whenever we have like this weird output, this is because we might have some hashing collision here, which means that this base and this mod is not big enough to handle everything. We could try to increase this one to an even bigger number. I'm not sure if this one. Let's see if this 40. This one works. Let's see. Interesting. So this one works. Yeah. So now, as you guys can see, no, this one works, right? Basically, if we choose a big enough number, this could pass. Or, like I said, like I mentioned in my previous videos, we can keep this one, but then we can have like a second hashing function, right? Right. Like mod2, this one, we can choose a different number, right? Like maybe -1, maybe. And then we're gonna need another base here. Basically, it's gonna be a total different set of hashing function here, right? And then another set of A here, of course, right? So everything has to be different. Base 2, meet mod2. Okay, so now we have current hash 2. So every time we just have basically copy everything, but this time it's for different hashing function. Base 2, path. This one is also the same. Hash 2. And then, so when we add into the hash set, we're gonna add the pair, right? Current hash 2. So this will also solve the problem, I believe. Yeah. If I run it again. A2. Oh, this one. Base, right? So the base should be different in this for this one. Seriously? This is not fun. The debugging the hash set, hash 2, base 2, hash 2. This should work. Let me see. Yeah, this one, that's weird. Probably this one, I guess. Yeah, I forgot to do the modular for the second hashing. So this, yeah, so this one should work definitely. Yep. So this one works, right? But as you guys can see, this one is fast. It's slower than the first one because this one we're doing double calculation, right? And it's a little slower, but it's still passed, right? With the first one, if we increase this one to a bigger number, so even with a single hashing function, it could work. But this is only based on the current test case, right? I mean, if the sorry, so if the test case changes, we might be hitting another edge case. Then that's when we probably need to adjust our mod or even add like another hashing functions to avoid all the hashing collisions, right? Okay. And as for the time complexity, right? So we have this L and R here. So this is the so everything is 10 to the power of 5. So this one is a log n, right? To binary search from 0 to n. And then the helper function, let's see. So the helper function, since the total path or total number is 10 to the power of 5, which means that this nested for loop here. So this nested for loop here is going to be a n, right? And then we have this is, and then we have for each of the parent outer for loop, we have this intersect. So the time complexity for intersection in Python, this one obviously is the minimum of the hash set A or hash set 2, right? Or hash set and hash set 2. So this one, this thing is a parallel. So that's why, it's still in the scale of n in this case. That's why the total time complexity is n log n for this problem. And I think that's it, right? Yep. So I think the first for this problem, the first step is that we have to realize that how can we efficiently find this longest common subarray. We have to be able to find to realize this is actually is a binary search problem, right? And once we find out the binary search the trends here, we need to know, in order to efficiently find the common path, we have to use like what? The rolling hash, right? And to do a rolling hash, we have to use like a 2 hash set to do an intersect, right, between them. And then in the end, we check if there's anything left. Then that's the helper function. Cool. I think that's it. All right. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.